Alright guys, any homework you guys wanna talk about? Crickets and cockatoos? No? Okay, so. So last time we talked about correlation. So today we'll talk about one new topic. It'll be rank correlation. In your syllabus, it mentions that we talk about one more topic, which is the beginning of chapter 11. We only have one class left. It's squeezing too much in, so I'm not going to talk about 11.1. So the last thing we'll talk about today is the end of chapter 10, which is rank correlation. And that will be all the topics for the semester. And then we'll basically review and answer any questions you guys have for the final exam. Yeah. All right. So last time we talked about correlation. And correlation was when we looked at two different variables and we wanted to know whether there was an association between those two variables. So remember, first day of class, we talked about the difference between correlation and causation. Causation means it's a type of correlation, but a much more specific type in that one variable is actually causing or inducing another variable. That's causation. But we're just interested now in measuring whether there's correlation or just an association between the variables. And another way to think about whether there's association is if you think about if the x variable were to increase, does the y variable also increase or decrease reliably? So last class we talked about a way to measure whether there's correlation, and we talked about linear correlation. In linear correlation, we try to fit the best possible straight line through all of your data points. So, for example, if this was our data points, then you can imagine the best possible straight line. And it goes through as many data points as possible, and for the ones that don't go through, they have the smallest distance from that straight line. So the best possible straight line might be something like that. Pretend that's a straight line. But even though this is the best possible straight line that goes through the points, it's still not a very good straight line because there's a lot of points it doesn't go through, and points it doesn't go through, the distance is still rather large from a line. So we measure how good of a fit that line is through R, the linear correlation coefficient. And if R is close enough to 1, then we say that R is a line of good fit. And we measure whether R is close enough to 1 by comparing R to R critical. So R critical, recall, is a number that you just get from your chart. So this is from the table. And then recall R, there's a heinous formula for R, but I don't expect you to use the formula by hand. Be comfortable using your calculator to calculate R. So each of these data points, you would enter in the x, y value for each data point, and your calculator will give you value for R. So once you get it, you compare it, yeah.
So another one that showed up on the homework was tables with two different lists of 50 variables, and I found out the calculator only goes to 42 for one side of the list.
Oh, okay. So in that case, you can always use technology. So you can use either import it to Excel if you have Excel, or G Sheets, Google Sheets, or you can use there's a built-in calculator through the publisher called StatCrunch. You can also import it there, but that question shouldn't have been there if it had 50 data points. So just to get through the question, just try to use an online correlation calculator and just import the data. But of course, on a test, you won't get a data set so large. Okay, so once you get the R value, to measure how good of a line the line of best fit is to these points, we compare it to R critical. If it's lower than R critical, well, let's start with, if it's higher than R critical, let's say, for example, if this had been 0.879, and let's say R critical had been and remember, R critical depends on your confidence level. So let's say you're willing to have a slightly lower confidence. Let's say 95%, where alpha is 5%. Then, if you're willing to have lower confidence, then the threshold, the R critical, is going to be a little bit lower. So R critical, let's say, will be 0.852. Let's say, for example, I'm just making numbers. But let's say that you had seen this from your table. So in this case, R is greater than R critical, is greater than the threshold to be deemed a line of good fit. So therefore, you can say that this actually constitutes a line of good fit to these points, so there is linear correlation. So you can say with 95% confidence, there is linear correlation based only on these sample data points. Any questions? Okay, so even without this line, just looking at these points, you could probably make the same conclusion that there is linear correlation between these two variables, x and y. The reason is because as x increases, y also, in general, seems to increase as well. So, and we measured that through the best straight line that we can fit through the points. But let's say that you had this case. So, just looking at this, would you be able to conclude whether there's correlation between these two variables? As x is going up, does y seem to, in general, also go up or go down? So as x goes up, either y consistently goes up, or as x goes up, y consistently goes down. So in this case, it seems like as x goes up, y is also trending up. So there should be correlation between these two variables. But if you tried to measure it, quantify it, using linear correlation, you'd only be fitting a straight line through the points. And in that case, the best straight line that goes through the points is probably something like that. And that's not a good fit at all. So if you looked at the R value, R will be something really low. So I'm just making numbers, but let's say 0.67. So in that case, if you try to compare it to any R critical from the chart, no R critical will be this low. So you'll end up concluding that this does not meet the threshold. So therefore, we ended up concluding that we can't just say, based on this limited sample, that there's no linear correlation, but we're going to lean towards saying that. So another way of saying that is do not accept or fail to accept that there is linear correlation, or an equivalent conclusion is do not reject that there is no linear correlation. So either one would be a correct conclusion. And remember, do not accept doesn't mean reject. You're just leaning towards rejecting that there is linear correlation. And do not reject doesn't mean accepting that there's no linear correlation, but you're leaning towards accepting that there's no linear correlation. Any questions? Okay, so this issue then, we know that there should be correlation between these two variables. But linear correlation is not giving us a quantification on that. So we need another way, a better way to quantify. And part of the reason why linear correlation isn't quantifying it for us correctly is that we know that as x goes up, if y were to trend up, there's lots of shapes, lots of curves that could depict that. A straight line is not the only curve that can depict that. So, for example, if you had something like this, you can fit a better curve onto that, like this. And this curve actually, if you remember from algebra, happens to be exponential. So this is an exponential curve. So by the way, what we mentioned last time is if you have data points that you're observing and you're trying to fit the best curve to the points, in general we call that regression. So regression is fitting the best curve to your observed data points. In the case of linear correlation, we're fitting the best possible straight line to those points. So that's linear regression. But a straight line is not the only possible kind of curve. For example, this would be an exponential curve, so you could have exponential regression. Or if your data points were like this.
Square root.
Yeah, very good. So this is either a square root or it's actually also logarithmic. So
The only way it's not gonna be a square root is if it's cubed, which means you have another set of data point on the other graph, on the other quadrant of the graph.
yeah, very good. So square root happens to be, this is the general shape of a square root, but square root is much more limited. If we bring it to the class of logarithmic functions, that's much more general. So we can say this is logarithmic. And so on. So in both these cases, as x goes up, y is also trending up. So in both cases, we should be able to conclude that there's correlation between x and y. But again, trying to fit the best straight line to the points is not giving us that proper conclusion. So one way that we can try to conclude whether there's correlation between the two variables is to try to fit every single curve that we know of, every mathematical model we can possibly think of, and toss it at these points and see if any of the models land. But first of all, that's very time consuming, and second of all, do we actually know all the possible models? So what if there's 10 different models that we've thrown at this and nothing is stuck yet? Does that mean there's no correlation? No, it's possible that we just haven't thrown the right model at it yet. So we don't want to just throw things at the data points and see what model sticks. So another way that we can do this and determine whether there's actual correlation between the variables is something called rank correlation. So that's the subject of section 10.3. So let's look at an example. So let's say you have these data points. these are the values of x, corresponding values of y. So just by looking at this, should there be correlation between these variables? As x is increasing, is y trending up or trending down? Yeah. Yeah, so as x is going up, y is also going up, definitively. So you should be able to conclude correlation here. But if we try to quantify that using linear correlation, which we've already talked about, go ahead and enter these data points in your calculator and see what you get for R. So again, this is measuring the best line that can fit through these points.
Yeah, R is 0.7385.
And so let's say we want to make a conclusion with 99% confidence, so alpha is 1, 0.
For 5 points, at 0.01 is 0.959.
So our critical needs to be 0.955.
959.
Okay, so you see that with 99% confidence, our critical or our threshold needs to be at least 0.959 for us to be able to conclude that the line is a good enough fit to the points. And now our value is only 0.73. So the best we conclude in terms of linear correlation is that we can't accept that there's linear correlation based on these sample data points. But we know that there should be correlation in general. So what happened was that we compared the values of x to the values of y, and it turns out that this is not a linear relationship. This turns out to be, if anything, exponential. So instead of comparing the values of x to the values of y, because our definition of correlation is basically as x goes up, does y also go up? So instead of comparing the values of x and y directly, let's compare the positions or the ranks of x and y. So that as x increases in position, does y also increase in position, in the order of its relative values. So what we'll do is we'll convert each of these y's and also each of the x into their relative positions. So having a rank or relative position of 1 means it's the smallest possible value. So of all these y's, which one has a rank of 1? Yeah, the 3. And which one has a rank of 2?
20.
Yeah, the 20. And so on. The rank of 3 is the next biggest one.
10,000.
Yeah, 10,000. And so on. It turns out that these are already in order. So these values would have these ranks or these positions. And what about the x's? Are we going to do the same thing?
They're labeled already.
They're already labeled, yeah. So the smallest x value has a rank of 1, so the value of 1 has a rank of 1. Value 2 has a rank of 2. So coincidentally, these values are the same as the ranks. So now that we've done it, we've ranked all the values. Now we're going to enter each of these pairs into our calculator. So instead of entering in the actual values, we're going to enter in the ranks. And then find the linear correlation coefficient for the ranks. And let's see what we get.
Yeah, R is 1.
Okay, so good. So you should be getting R is perfectly 1.0. So that means if you compare the ranks to each other, you're going to get a perfect linear relationship. So this is what we call the rank correlation coefficient. After that, after the guy who came up with it is Spearman. So sometimes his name is included, sometimes it's not. But the variable that denotes this is R sub S, and S is for Spearman. So R is just the linear correlation coefficient, R sub S is the rank correlation coefficient. That's found from ranking all the X's and Y's, and then entering those new ranks in your calculator to find the linear correlation coefficient for the ranks. Okay, any questions? So just like before, after we get this R value, we want to know whether it's close enough to 1 to be considered having correlation. And so, just like before, to decide whether it's close enough to 1, we're going to use a table for that. So if you look in the, I think the same page as your rank correlation, you'll see right next to it, it says Spearman rank correlation. So same thing as before. There's going to be an RS critical. And again, it's going to be based on your confidence level and alpha. And for a set number of data points like 5, go to n is 5, and then look up the alpha that you want, and then there's going to be R critical. So let's just do it for this example. So n is 5, and let's say we want alpha to be 0.01, so 99% confident.
It just has a dash.
Oh, okay, so that means that 5 data points isn't enough. So let's say we have 6 data points.
Also a dash.
Okay. So what's the first non-dash?
The first on dash is 7, and
Okay.
929.
Okay, so let's say we had 7 data points. Let's actually do it so that you see. So let's say that this is 7 million, let's say 70 billion, 70 million. And let's say this is 80 million.
Million, billion, trillion?
Yeah, so basically, as X goes up, Y is continuing to go up. And so again, intuitively, we should be able to conclude that there is correlation. And again, if you had entered this in your calculator with the new ranks, this would still have a rank of 6 and 7.
It would still be 1.
And over here, you'd still have a rank of 6 and 7. So R would still be exactly 1. And then R critical for 7 data points would be
969.
0.969. This is for alpha.
Correction, 929.
19.
I'm not trying to be smart aleck here, I'm just trying to figure out the right answer on this, but if you already have an RS factor and it's a perfect 1, why do you have to look up the table factor?
Oh, we're just going through the general procedure. If this had not been 1, then we would have that. But yeah, so clearly if this is the maximum it could possibly be, then we wouldn't have to use the table. Okay, so in this case, because your R value exceeds R critical, we can conclude that there is correlation between these two variables. Specifically, there's rank correlation, but rank correlation is just a kind of correlation, so you can conclude that there is correlation between these two variables, X and Y, just from these 7 data points. Any questions?
I have them, but I don't really know how to voice it right now.
Okay.
Doing the homework problem they gave you, they basically 2 lines of data so that you can rank them. They did not line up as easily as this did, and then it went into formulas on how to solve them.
Yeah, so the formulas, there is a rank correlation formula, but I didn't want to present that because this is much more intuitive. This actually describes what rank correlation is doing. So basically rank them first and then find the linear correlation of the ranks. Don't worry about any formula. But you'll get the same answer using the formula. Yeah, so let's look at an example. So yeah, so in this example, it seems almost too contrived that the values and the ranks are lining up perfectly like that. So let's do an example where that's not happening. Okay, so let's do this example. Let's say that we wanted to see whether there is a relationship between the rankings of TVs in like Consumer Reports. So TV ranking versus the cost of the TV. So basically the question is, if the TV costs more, does it mean it's necessarily better? And so let's say that these are the TV rankings. And this is the cost in hundreds of dollars.
Dang it, you get size in there.
Yeah, yeah.
That makes it a lot more fun.
Yeah, the ties are actually not instructive, so let me get rid of the ties. Okay. So let's do it both ways. Ultimately, we want to know whether there's correlation between these two variables. And so let's first try to see if there's linear correlation. Plug the data points in as is and see what R is. So this is so this means that if the line of best fit is actually a good fit, then it would have a negative slope, it would have negative correlation. But this isn't a line of good fit to begin with, it's only 0.23. It's not gonna be considered close enough to 1. So we would not be able to conclude a correlation here. So let's go ahead and find R sub S, which is the Spearman rank correlation coefficient. So we're gonna convert each of these values into their ranks instead. So let's start with the Y's. So the one that has rank of 1 would be the smallest one.
Yeah, so you're gonna have, going from your left from 1 to 10, your Y's over 1 will be 5, 2 will be 10, 3 will be 6.
Okay, so let's just start with the Y's. So what's the smallest Y value?
Your smallest Y value is 14.
Yeah, so that'll have a rank of 1.
2 is 16.
Yep.
3 is 20.
20.
Number 4. Very bottom is gonna be number 4, 22. Number 1 up there at the top, 23 is number 5. Third down is gonna be number 6. 25 will be number 7. 32 will be number 8. 40 will be number 9. 50 will be 10.
Okay, great. So these are all the new values for Y. And then you do the same thing for X's, but then you notice that the X's are already in their ranks. But just for due diligence, we can convert all their values into ranks. And now for each row, what we'll do is we'll enter in the new values for each row into the calculator. So for the first row, you enter in a rank of 1 and a rank of 5. The next one you enter in 2 and 10, and so forth. So you enter the rows as is, but with their new values for the ranks. So,
R value of negative 0.2606.
so we see that with this rank correlation, we're not doing any better in terms of correlation.
2606.
So with this new measurement of a rank correlation, we're not doing any better in terms of correlation. So you can conclude that based on this data set, we can't conclude correlation. So we fail to accept that there's correlation. But again, fail to accept doesn't mean we can never accept correlation in the future. If we observe more data points, it just means for now with this data set, we can't conclude correlation. Any questions? So this idea of rank correlation, because we're taking into account the ranks and not just the values of the variables, we're able to capture a lot more different models than just a linear model, straight line model. So we're able to capture all these different situations. So, and more, so let's say we had like this. So a rank correlation quantifier is able to capture all of these different situations that describe correlation versus just a straight line model. So why do you think anybody would use a linear correlation coefficient, just R, as opposed to just jumping straight to R sub S? why even discuss the linear correlation coefficient at all to begin with? Why not just jump into this? Because this captures more possibilities of correlation than just a straight line.
Linear is most common.
Yeah, linear is most common. And what else?
Honestly, I think it would be what you're trying to measure.
Let's say we just wanted to determine whether there's correlation. And also, if there's correlation, maybe try to make predictions.
It's not always necessary to take this next step. Sometimes we can stop at linear.
Okay, but let's say that linear correlation concludes that you can't fit a straight line through the points. That could mean that you can't fit any good curve through the points, or it could mean that you can fit one of these curves. So why not just start here and see whether any of these are possible?
I think it just gives you an idea that there is a fit, you just don't know what it is yet. You have an idea of finding out if there is a correlation basis at all.
Okay, good. So the rank correlation tells you whether there's correlation at all, whatever model this is. But then, why do linear correlation?
If it is linear, then it might be more accurate to use linear correlation.
Okay, you're on the right track. Good. So this just tells you whether there's correlation, yes or no, but it doesn't tell you which of the models that actually is. It just tells you yes or no, right? Linear correlation tells you specifically that it specifically is a straight line model, and knowing that it's a straight line model, now you can fit a straight line to those data points and actually make predictions based on the equation for the straight line that you fit. So if you know specifically that it's a straight line, you can actually go further and make predictions based on that straight line. This just tells you yes or no whether there's correlation or not. It doesn't tell you the specific number. Any questions? All right, so that's rank correlation. Basically that's it. That's all the topics for the semester. Congratulations. So the time we have left,
Your method of solving that was way easier than using the equation. The equation gives you the same answer, but it's way easier.
yeah, okay. And also, this way gives you a better understanding of what's actually going on. You rank them first and you try to fit a straight line through the ranks, as opposed to just using some random formula.
Yeah, the 1 minus the 6 sigma delta squared over number and brackets with the number squared minus 1.
Yeah, so don't use that point. Okay, good. Any other comments or questions?
So you're uploading it tomorrow, right?
Uploading what?
The-
Oh, the test. Yes, yes, yes. So the final exam, it'll be approximately 30 questions. Well, 35 questions in there. So there'll be more questions than the typical unit tests that you've seen, where those have been like 25 questions. So I'll give you guys a little bit more time, not necessarily that you'll need it, so I'll give you 4 hours. You should not feel that it necessarily takes you 4 hours, so don't feel like you're obliged to sit there for 4 hours. But the 4 hours is just so you can be reassured that you don't need to rush and you can Check your answers if you need to. So, also, keep in mind, remember that the exam is cumulative, covers all the material. But it'll probably, have more weight towards the questions that you haven't been tested on. So, chapter 8, 9, and 10. You haven't been tested on, so these will have more weight. Okay, so just like before, it'll be open book. I'll allow open notes. Also, calculator. You're expected to use a handheld calculator. That's not anything with Wi-Fi. None of the questions will ask to use technology, so you don't have to worry about getting an online calculator or getting a fancy graphic calculator. But if you have a graphic calculator, you can use it. Again, this will be proctored through AutoLock. Any questions so far? Okay.
Deadline? Because
Oh.
at the end,
Yeah, so this will be open after class. So I'll make it due Saturday night, so you have, some time to study if you need. So due Saturday night. Grades are due for me Monday morning. So Saturday night by midnight. Any questions? All right, let's start reviewing. So the stuff that you haven't been tested on is chapter 8, 9, and 10. And basically, the bulk of that is hypothesis testing. And as you've seen, all hypothesis testing questions follow the same framework. And if you're comfortable with that framework, then hypothesis testing will be really easy. So basically, you have a claim, and that claim will have some measurement in it, whether it's a claim that has one proportion, whether it has a mean, whether it has a standard deviation, or that claim could have two population proportions, or two means, both independent and dependent. So dependent is matched pairs. Yep. And then technically, linear correlation is a kind of hypothesis test. So if your claim involves rho, which is a linear correlation coefficient, so this is rho, not p. So your claims on hypothesis testing can involve any of these things, any of these measurements. And what distinguishes them is the underlying distribution. So there's a shape of a certain distribution that goes with each. And in each distribution, there's a dividing line between the body and the tail. So that dividing line is the
Critical.
critical statistic. We state statistic in general, but that statistic could be a z-score, a t-score, a chi-square score, and so on, depending on the underlying distribution. And so that's the dividing line of where the tail is, and then the whole point is to look at the observation and decide whether the observation is in the body or the tail. So the observation will have a test statistic. Test statistic will always come from a formula that you'll have access to. Critical statistic will always come from a table that you'll have access to. And then you just compare the test statistic to the critical statistic to decide whether the observation is in the body or the tail. If it's in the body, you reach one set of conclusions, fail to reject HO. If it's in the tail, you reach another set of conclusions, reject HO. And basically, that's all the hypothesis does. Alright, so the main thing is, depending on what measurement you have in the claim, that decides what the underlying distribution is, and also decides what table you use to find the critical statistic. And depending on the measurement, that determines what formula you use for the test statistic. But essentially, that's it. Any questions on this? Should we go over one at a time, which distribution, which
The first one is gonna be Z, the second one will be your T's, the third one's gonna be chi for your variance or deviation. It follows through with the same for P is also gonna be Z, because you're doing the same thing, and your means will be another type of T. And how you figure it out is dependent on whether you're doing matched pairs or if it's two independent samples to compare them to make your statistics.
okay, excellent.
And then your whole part about row on the bottom is depending on what they're asking for, be it spearmint or not, how you're calculating your R value to determine its correlation.
So the table you would use for the row would be the rank the correlation coefficient table. Okay, good. So this is linear correlation coefficient. Okay, so this tells you the tables that you're supposed to use. So the tables will allow you to find the correct critical statistic. And then each one will have a formula. Should we write the formulas out? So, I don't know if it's easier to write the formulas or maybe write just the sections in the book. But I'll start with trying to write the formula. So, if the claim involves one population proportion, then the formula that we use for z-test
It would be Z alpha divided by 2 multiplied by the square root of x minus n divided by the number.
yeah, so z-test has two different formulas. One's the book, one's the one we talked about. The one in the book is this one. So that's the z-test. And then the one for t-test. And then the one for chi-squared. Let's see. for two proportions. Let's write that here. So in the case of the independent one, let's do that first, independent. And then, dependent match pairs. And then, linear correlation, we talked about this row value, the R will be found from your calculator. But basically, those are the formulas we talked about to find the test statistics, no matter what hypothesis tests you do. So, yeah.
From the other formula that you gave us, for the independent, you said P dash, does it matter if it's P naught or P dash?
Oh, which one?
Independent, it's X, not P dash, I mean X dash, X one dash and X two dash.
Yeah, so these are the means. I forgot to write down the formula for the two proportions. That's the one you're referring to. So the ones for two proportions is, yeah, so I think this is the formula that you're referring to, which has to do with two proportions.
I was talking about the X, like does it have to be dashes, cause you have dashes on the, when we talked about the other day.
Dash.
For
So
the
it's the
X,
X
cause
hat,
you go
X
X
bar.
bar, does it matter?
Oh, yeah, it should be X bar, I think. Okay, so with each of these test statistics, you would just compare it to t-critical to see whether the observation was in the body or the tail, and then make your appropriate conclusion. Remember, we also said that you should also be comfortable finding the p-value, but the only one that I'm gonna ask you to find the p-value for is for the case of using the table where it's a z-score table. Because all these other tables, the areas are spaced very far apart, so it's hard to make a good approximation using those other tables. But for the z-score table, because the p-value involves finding an area, the areas in the z-score table are spaced very close together, and you can get a good approximation for the area. Okay, so be comfortable finding p-value for z-score tables. You guys comfortable finding p-value? Should we review?
For just the Z, I will say yes.
Just as the
For just the Z, yeah.
Yeah,
I'll
yeah.
say my test rate.
Okay, good. For the other ones, chi-square table, t-square table, you're not gonna be required to find p-value. Essentially, it's the same general approach, find the area in the same direction as the nearest tail, and then multiply by the number of tails. But for these other tables, it's not it's hard to find an exact or a good approximate area because those tables are not laid out, with precise areas.
Can we do one?
Yeah, sure. So let's say. Let's say we have this test statistic that has. A z-score, a z-test of 0.02. And let's say that you have a one-tailed test here, and it happens to be a left tail. So let's say I ask you to find the p-value. So step one will be to find the area in the same direction as the nearest tail. So relative to this t-test, you either have a left area or right area, but which area is in the same direction as the nearest tail? Yeah, there's only one tail, so that has to be the nearest tail. So relative to this test statistic, you want to find a left area. So go ahead and look up 0.02 as the z-score. And then find the left area. Okay, so the left area is 0.5080. Looks good. And then that was step one of hypothesis testing. Step two is to multiply that area by the number of tails. So in this case, you're just multiplying by one, so it doesn't change anything. So the p-value in this case is 0.5080. So let's say that you would add basically the same situation. But now you have two tails. So then find the p-value.
In this table, you said the nearest tail is, would you say right?
Okay, so that's something, so go ahead and think about it and we'll answer it again. Okay, let's talk about it. So the first step, the calculating the p-value is relative to the test statistic, find the area in the same direction as the nearest tail. So relative to this z-test, the nearest tail would be on the right or the left?
Right.
Okay, very good, the right. And the reason we know that is because z-test is currently on the right side of the distribution. How do we know that?
It's greater than 0.
Okay, very good. So right at where this peak, or the center is, the z-score has to be exactly 0. Because it's 0 standard deviation from the mean, and the peak is the mean. So this z-test is greater than 0, so it has to be the right of the distribution. And so the nearest tail has to be a right tail. So the first step of finding the p-value here is finding the area to the right. So before we find the area to the left, so the area to the right will be subtract from 1. So this will be 1 minus 0.5080. That should be
1920. And we're gonna multiply by 2 tails, right?
very good. So that was step 1, find the p-value, find the area in the same direction as the nearest tails. Step 2 is multiply by the number of tails. So we have a 2-tail test here, so we're gonna multiply that number by 2. So the p-value here is 2 times 0.4920. So one thing I wanted to emphasize is that we talked about how to calculate p-value, we talked about how to interpret p-value. So, for example, this p-value here in the first case, if it's 0.5080, and your confidence level, let's say, is 95%. Okay, what would your conclusion be if the p-value is 0.50?
You would reject HO because the p-value is greater than alpha?
Yeah, very good. Well, so in this case, what's alpha?
0.5.
Yeah, 0.05 is alpha. So we're gonna compare this p-value to alpha. So if the p-value is low, the null must go. But in this case, is the p-value low?
It is not.
It is not low. So if the p-value is not low, the null does not go. So in this case, fail to reject HO. So that's calculating and interpreting the p-value. But I want you to leave this class where if somebody asks you on an elevator, what's the p-value? Instead of getting bogged down in all these details, I want you to be able to give a short answer. So what do you think the p-value is if somebody asks you on an elevator?
The p-value is basically the percentage that you get from the information you have to produce a data point that can be evaluated.
Basically, okay, good. So remember, the p-value is you have a certain observation here that has a test statistic. And the p-value is the area in the same direction as the nearest tail. But if you explain that to somebody on an elevator, they'd ask, well, what's a tail and why does it matter? And so forth. So basically the p-value is, in the context of this distribution, you're assuming that HO is true. So if the null hypothesis were true, how likely would it be to observe your observation? That's basically all a p-value is. And if your null hypothesis is true, and the p-value is low, that means it's very unlikely to observe that observation if the null hypothesis is true. And so therefore, if it's that unlikely to observe your observation, if the null hypothesis is true, then the null hypothesis can't be true. So that's why we want the p-value to be low. And maybe to help reinforce this, so So there's a real life example of this. A few years ago in the news, there was talk about the Higgs boson. You guys remember that?
Say the last part of that again. Higgs boson. Yep.
Yeah, the Higgs boson. This is also in the news called the God particle. So this is a few years ago in the news, and so what this is that a long time ago, in the 50s, there was a scientist who predicted that there was a particle that was responsible for generating mass in the universe. So that's actually, that would actually be big news if it were true, because for a long time people thought that mass couldn't be created or destroyed, and yet there's somebody saying that there's a particle that actually creates mass. And so the media got a hold of this and dubbed this the God particle, just to sell papers.
Apparently it worked.
Yeah. So in order to test this idea of whether this Higgs boson or God particle actually exists, people in Switzerland created this giant tunnel that was able to accelerate particles at a super high rate. And then when they're able to accelerate these particles, they theorized that this Higgs boson would arise from that. And so the point of this is that they had this null hypothesis that the God particle didn't exist. And it turns out that their p-value ended up being so this is basically 1 times 10 to the negative 7. So basically this is saying that if it's true, that the null hypothesis is true and the God particle doesn't exist, how likely would their observations be? And it turned out that their observations would be extremely unlikely, almost impossible, if the God particle didn't exist. And so if what they actually observed was this unlikely, then this assumption is probably wrong. And so that's what they were trying to get at. In the end, they were trying to reject this null hypothesis. And so when they first discovered this and got this p-value, all the scientists were like, jubilant. And they were like screaming in the news that they were 7 sigma or 7 standard deviations away because their p-value was so low. And their p-value being low means that it was super unlikely for this to happen if the null hypothesis were true. So therefore, the null hypothesis could not have been true. Any questions? Okay, so that's p-value. Any questions on this? Okay. Okay, so any questions on the stuff that we covered after Unit 2, chapters 8, 9, or 10? Okay, good. So I was gonna ask you any topics that you guys wanna talk about right away, and it seems like there's a probability,
That it will be on the exam? Yeah.
Sure, sure. So the issue with probability is you'll just be asked to find the probability of some situation, right? But ultimately, it'll have to do with one of the principles of probability that we talked about. So let's talk about the concepts of probability that we talked about. Let's review that. So we talked about the classical definition of probability. Where to find the probability of a desired event. It's equal to the number of desired events divided by the number of total events. And then we talked about the addition rule. Addition rule had to do with probabilities with events joined by or. So if you see a probability with a situation that's structured with events joined by or, then you can apply the addition rule there. And the addition rule is you can break these up into separate probabilities, but joined by addition. And at the end, you have to subtract out the probability of any overlap between the events. And then we talked about multiplication rule.
That's for events joined by and.
Yep, joined by and, which means they both have to occur together in the same situation. So this would be the probability of A times the probability of the second event, given that everything before it is assumed to be true.
And that's probability of alpha multiplied by the probability of B given alpha, right?
Right.
Okay.
So the multiplication rule in general requires this conditional probability. In general, but sometimes that conditional probability, if these two events, B and A, are independent of each other, then you can ignore that condition and just use the probability of just B without the condition on it. So again, if A and B are independent of each other, then you can ignore this condition, and this conditional probability just becomes probability of just B. So let's review that a little bit and give you guys some intuition. So let's say event A here is that it's sunny outside. And let's say event B is that there's currently people at the beach. So we want to know whether the events A and B are independent of each other. So there's two ways you can answer this question. One is just to ask, if one happens, does it change the probability of the other? So for example, if it's sunny outside, does it affect the probability that there are people at the beach?
Yeah.
Yeah, so if it's sunny outside, the probability of people at the beach will be higher, versus if it's not sunny, the probability of people at the beach will be lower. So One affects the probability of the other, so therefore these events are not independent. This would be no. So that's one way that you can answer that question of whether these two are independent. Another way is a more formal mathematical approach, which is to ask if the probability of B given A is the same as the probability of just B. So is this conditional probability the same as ignoring the condition? So if it is the same, then these events are independent of each other. So let's go ahead and try to answer this for these examples. So the probability of B given A, which is currently there are people at the beach, given it's sunny. So what do you think that probability is, which is given it's sunny, the probability of people at the beach?
Pretty good.
Almost 100%, virtually 100%, right? So let's say 1. But let's look at the non-conditional probability. What's the probability that there are currently people at the beach, period? Regardless of the condition, regardless of whether it's sunny, or if it's cold, or whether it's dark, regardless of any condition, what's the probability that there are currently people at the beach?
0.5.
Yeah, maybe 50%, or whatever, 60% or whatever, but it's definitely not 100%. So because these two probabilities, the conditional versus the non-conditional probability, are not the same, these events in the conditional probability are not independent of each other. If they were the same, then these events would be independent. Okay, so now we reach the same conclusion that no, we don't have independence. And so that's why this conditional probability matters, is because in a lot of cases, the events are not independent, but if they are, then you can ignore the conditional probability. Okay, so let's multiplication rule.
In the probability part, there were a lot of questions that gave several variables, and it was trying to decipher what variable it was actually asking for.
Right,
Is there a way to try to move that down for better understanding?
Yeah, so let's summarize the underlying rules first, and then we'll talk about how we know which rule to pick. So, next rule we talked about was rule of complements. Where the probability of a desired event is 1 minus the probability of its complement. Another probability rule we talked about was binomial probability, where we have a probability of X successes out of N trials. This would be that formula we talked about. We talked about another situation where if you ended up finding a summation of probabilities of these structures, where you have a probability of a number of successes out of another number of trials, each of these are binomial, you find yourself adding up multiple binomial probabilities. So,
Where the mean equals m times p, and sigma is the square root of mp cubed.
yeah, good. So adding up multiple binomial probabilities where the binomial distribution, the mean and standard deviation are what you just gave. Then here you would fit a bell curve onto the underlying distribution, where the mean is NP and standard deviation is the square root of NP cubed. So this is fit bell curve. Where mean is NP, standard deviation is square root of NP. And then just before that, we talked about if you have x being given as normally distributed, or a bell curve, then find the probability of x being less than some number. This is just finding the z-score, looking it up in the chart. And then the last case we talked about finding probabilities was when the central limit theorem was involved. And we had to find the probability that a sample mean was relative to a number. And this was the central limit theorem. So basically, these are the mathematical rules we talked about for probabilities. So each rule has a certain requirement or certain structure for using it. So the classical definition is the most general one. If you have a desired event and you're able to count up all the desired events and you're able to count up all the total events, then you would use this one. And then the addition rule, if you have a probability with two events joined by or, then you would be able to use this one. If joined by and, you'd be able to use the multiplication rule. If the structure is, you know the probability of the complement much easier than the probability of what you're trying to find, then you would use the rule of complements. If you have a probability with the structure, a number of successes out of another number of trials, you would use this binomial probability formula. If you find yourself adding up multiple binomial probabilities and using this formula over and over and adding them up, then you would fit a bell curve onto the underlying distribution instead and calculate the z-score using this mean and the standard deviation. If your variable is told as being normally distributed, and you're just trying to find the probability that variable is less than or greater than the number, then you find the z-score, look it up in the table. And if you're trying to find the probability that a sample mean of values is relative to a number, then that would be the central limit theorem, where your mean is the original population mean, and your standard deviation is sigma over the square root of n. So to decide which of these to use when you're finding probabilities, you'll have to understand what the structure for that probability needs to be, whether it's even applicable to begin with. And just because it's applicable and you can use it doesn't mean it'll be helpful for you to use to actually solve the problem. Because sometimes, if you have a probability that has a whole bunch of ors, mathematically, yeah, you could use the addition rule, but you might find yourself adding up hundreds of probabilities, in which case it's not feasible for you to use this rule, even though it would work and give you the right answer. So you'd have to back up and see whether you could use one of the other rules, like the rule of complements, for example. So to decide which rule to use, you have to see whether the structure pertains to that rule, but also it requires a little bit of exploring to see whether it's even helpful for you, whether you'll be led to a dead end or not. So that's the hard part, is being patient with the exploration and
figuring out what they want. I mean,
Yeah, yeah.
the only place that really honestly to me in my mind becomes hard is between 7 and 8, because normally distributed, right? And then they want something that literally falls directly on what that standard deviation would be. You spit it out based on the empirical rule, but it's not right, because they wanted to use the central limit theorem and actually break it apart. And
Okay, so let's talk about the difference between these two then. So in this case, you're told that this variable, the individual values, each value of this variable is normally distributed. For example, each one person's IQ score, each one person's weight, that number is distributed normally. What the second one is saying is that if you have a sample of values, then the average of the values of that sample will be normally distributed using the central limit theorem. So in this case, if you're told, for example, heights are normally distributed, heights of women. You could be asked, what's the probability that the height of one woman is less than 5'10", for example. And so that would lie in this case, where you just calculate the z-score of this variable representing one individual value. And the mean and standard deviation would have to be given to you. Find the z-score, look up on the chart, and you're done. This case, instead of talking about one woman, you're talking about a sample of more than one woman. So in this case, you'd be saying, let's say you select a sample of 20 women. And then from those 20 different values representing heights of women, you would find the average of those 20 numbers. And that's what this would represent, is a sample mean. So up here, this x represents one individual value for your variable x. This represents an average of more than one value for your x's. So one way to get an idea of which one you're dealing with is, at a given time, are you only looking at one data point, or are you looking at a sample of data points? And if you need to find the average of that sample, that's dealing with the central limit. Okay, any questions? All right, so this is a good question, basically, which is, how do you know what probability rule to use? And the short answer, if it were to be reduced to a short answer, is that you don't really know. You have to first explore all the probabilities rules that we've already talked about, and then kind of explore a little bit, do some trial and error. Ultimately, you might only have to do trial and error between two candidates, because a lot of the candidates won't fit the structure that you need. Any questions?
Tomorrow is gonna be basically a day of coming in for review and different questions, right?
Yep, so. Oh, I thought today was Thursday. Oh, okay. Yeah, tomorrow we'll be reviewing again, so test won't be open until tomorrow.
Man.
Do you want it open today?
It's not gonna help one way or another, it's like.
Yeah, no, we'll have our last class and I'll open the test.
Yeah, I mean, if it would benefit somebody back there, sure, I mean, but it feels weird if somebody has the ability to start bringing test questions into class and then you have a way of compromising the test. I would not recommend it unless everybody agrees with it.
Yeah.
That would be awkward.
Is it still due Saturday or Sunday?
Saturday.
Saturday.
Well, there will be less hints on the questions on the final about what direction we go than the previous tests. What we were required to like use a little bit more intuition.
You're asking whether there will be hints on which approach to take?
Yeah.
No, it'll be similar to the.
Similar.
last test.
Now, this in general, this was good.
Okay, good.
You can keep it.
Sure. What about this? I'm sorry. Have a good day.